general slicing or the general cross-section method. And you guys need to start triggering up a lot of your the visual sense, okay, for this topic particularly. All right. So, you guys ever observe the roof of a house?
Yes.
Okay. In the most basic form, it looks like this, right? So, there's a base being a rectangular shape, right? And then we built those triangular structure on top of that, but those triangular structures are parallel with each other. You guys seen things like that before? Okay. So think about those. See, they always follow that rule being a triangular. If they stand up, straight up, right from. So the idea now that on this rectangular surface right here, those triangular structure right there, they stand up as a slices. See what I'm saying? Those are slices, right? Being vertically standing up. The slices are, I mean, on that flat floor right here, those slices are parallel with each other. So think about it. If we're placing our eyes, look straight down like this, and what we have in front of us is a rectangular shape, right, with the slices standing like that. I mean, the number one thing is the slices got to be parallel, right? The slices are parallel, indicating that they are in one same direction altogether. I mean, we can put the slices in your area at the base. You can put the slices like this. That's okay too, right? But a lot of times, they've got to be parallel. They've got to be in the same direction. You know what I'm saying? And then on top of those, slices like that, right? With those slices, right? So each slice is a figure. Okay? So all slices, right, are the same figure. That's the idea of how you look at the structure of those house roofs, right? Before they actually put the actual cover on top of that, right? And there's no structure like that. See, there's a rectangular base, right? There's a base right there, and then there's these slices standing. I mean, they are parallel with each other, but they're standing vertically up, right? It's standing perpendicular with the base. Yeah.
What do you mean by figure?
So they gotta be the same. So if it's a triangle, then it's got to be all triangles again. Okay, so that's what it means by the same figure. Okay. Sounds good. So, more detail, slices are perpendicular, always. Perpendicular to the base. Of course, there's a base area without any need to mention. Got that there? Okay. And so now in that way, to calculate the whole volume, so think of it, where's the calculus coming in? Each slice here again got a thickness, right? And so each slice here on its own here is a cross section. See, the slice is also a cross section because if you're looking straight at the slice here, if you place your eyes here to look straight at the slide here, it's a cross section, right? And then it's being a cross sections again. You can go cross sections area. You multiply that with the thickness. What does that give us? It gives us the volume for one slide, right? For one cross section. See what I'm saying now? Right. This is the. So all this here is the volume. The volume of one slide. Right? There's some thickness, right, in the volume of one slide. Then in that way, what's the calculus doing here? We're accumulating again from some start, right? To the end right here. We're accumulating all of the volume, slice volume again, right? Accumulating it all from some beginning point to the end point again. We're gonna get the total volume of the whole See the whole roof shaped like that. Am I making sense? Those are a few characteristics you can remember. So the slices have to be perpendicular to standing straight up from the base, right? And then the slices are parallel with each other. All slices are parallel to each other. Okay, and then each slice is a figure itself, and they have to be all the same figure. It's not. It cannot be. I mean, we don't deal with that kind of situation where it's a circle here, and the next slide being a square, and the next slide being a rectangle, something like that. It's gonna make it. It's gonna make lives too hard for us. See what I'm saying? That's why. Yes, each slice is some kind of figure, right? But then in the end, we want all slices are of the same figure. Sound good? Because those come up with some kind of regulation for us. So right here in this problem, of course, how much volume that's filling in a roof like that, it's easy. You don't need to go to calculus to get that. You see what I'm saying? No? But just right from there, let's apply calculus and learn how we can calculate the volume with that. So we don't use the high school geometry to understand it here, but we use calculus for this. So let me now really bring up that problem again. Right? So you got the base area being a rectangle, right? Base here is a rectangle. You guys want to name some dimension for here? What's your name? What's your own name? This is dimension 10 by 4. 10 by 4? I'm cool with that. 10 by 4. Sound good? Okay. And then so now on top of that, and definitely when it comes to each problem, we got a lot of times to have to mix between wording, right, and figures coming along with that. Okay? And so that's the base. Now I'm going to tell you each slice, right? Each of the parallel what are the heights?
That's the dx, right?
Oh, yeah. Don't worry about the dx or whatever.
2.
Okay. So now when, of course, it's a space figure, so don't blame me for being a little off scale, okay? So
you have 4 by 2 now, so that's great.
Okay. You don't know? So the height, and it's an isosceles, that's why this height dropped right in the middle of it, right? You guys know it, right? So some of the characteristics of these basic figures, you gotta still remember, you gotta still know it. So that height right there is 2. You name it, right? So now we're gonna learn to calculate this whole volume. So think about it at every instance, right? I'm only drawing a few right there. Right? See, we got a lot of slices, right? I can only draw a few, but see, these are all of heights 2, right? And then those are all having these slices. So that's why you can see that as we accumulating all of those slices, right? We got the whole volume of that whatever space inside of that roof structure. You know what I'm saying now? So let's calculate that volume. You want to calculate it? Right. So now the first thing I'm doing, see, this is where we gotta have to start bringing it a lot more flexible than this. Just think about, and right here in this promoting problem, when you're working with a live problem that's right here at your base, right? Right here at your base, you have your choice to put that base area right on the x and the y axis right here. Think about put that length right here. 0 is here, 10 is here, right? And then that's the 4. The 4 is on this end. You guys follow it? So there's a y-axis, there's the x-axis, and whatever, some other imaginary axis. I mean, I'm not talking about the imaginary number, right? But there's some imaginary axis that's going in a space setting with that. So there's a floor right here, and then the x-axis is on that floor, right? So your rectangular base is here. But you see, the idea now is that when you place your stripes in parallel in this way, how we see that through the picture, then what's the thickness of each of your slides here?
Yes.
There you go. It's all about, and And so here we have complete control over how we set up our thickness, all depending how we place our figure, right? So if we purposely place a figure along the x-axis like that, see what I'm saying up? Okay, and the thickness is the x. Are we good? Okay. And so now, and each one of these, so anywhere that you place your slide here is an x value, right? And anywhere you place so the x value is inside anywhere from 0 to 10, you guys know with, but anywhere you place your slides, right? It's right at the one spot on the x-axis. That's why it's at some x value. You guys agree with me on that so far? Okay. And so now think about it this way over here. Anywhere that you put your slide, right? The height is being 2, right? So you got a slide like that being a triangle. Okay. So how do we calculate the area of a triangle? Because remember, the fundamental here is that it has to be, the fundamental says we need to first find the volume of one slide, right? By multiplying the cross-section area with the thickness. We already figured out the thickness, right? We just need to figure out also the area of that cross-section right on each instance, okay? Right on each slide. Are you with me on that? So now that's why I think about right now if we're right here at any one of the slides, even though at some x value, but think about it, how much is the base length of here? How much is that base length?
Yes.
No, the x is the thickness. Now I'm talking about the actual base length here.
4.
It's just 4, right? So 4. What's the formula for getting triangles? Yeah.
Base 10 times, so 40 divided by 2, and then what would you
No, not 40 actually. For this triangle.
Oh, 4.
4, just 4?
2.
Well, yeah, times 2 the height, right?
Yeah.
Times 1/2. So that's
the dx there.
Yeah. So the dx is just the dx later on is the thickness, right? But right now it's the area. Right? The area of the slides, right? See what I'm saying there? Right? So here the area is thankfully is still completely independent with the x, right? Anywhere you put your slides, you call it as an x value on this axis right here, but your area remains the same. See what I'm saying? No? In some other problem, it may change. Who knows? Right? So now in this way right here, you're gonna multiply it together. 1/4, and then 4 times 2, making it. That all equals 4 as boss said. So 4 is being the area of one slice, right? But multiplied with the thickness, dx. See what I'm saying? No? And then now that's a volume for one slice, right? We're going to accumulate all slide volumes here, from where to where. I place a figure, and we had our control like that, right? So we're accumulating from where? Starting at the 0. See what I'm saying now? And ending up with the last stop right there, right? In 10. Are you following me on that? So now that will give us the volume in that. Right? So iterating this, right? Now taking the accumulation by doing the usual integration work here, it gives me what? That becomes a 4 for x, right? As a function in terms of x, we're evaluating from 0 to 4. Thank you. Yeah. So that's making it actually 40, right? So let's check. So we did that with the calculus methods here, the calculus methods, using cross-section and accumulating the cross-section. But like I said, we didn't need to for any one of us. We don't need to wait to calculus to know how to find this volume here. As a matter of fact, what kind of figure is it? It's just a triangular prism, right? So if you putting it standing up like this. It's just the base area of one triangle. So 1/2 times 4 times 2. All we do is just actually multiply with the height here. That height being 10, right? There you go. So all together is 40. Right? So we already had a way to check the answer, but this work here is using the calculus approach. That's all what I'm saying. But of course, after this problem is only promoting the idea, right? But after this problem, of course, life is not always that simple. Things just go. The good thing about this problem is slice area here stays constant, right? So that's why it's easy to get to see the same area throughout the whole thing, right? And the more you put that into slices, the more precise you get, right? With that total volume. You know what I'm saying? Huh? Okay. Now I'm going to just simply change the situation and you will realize the impact here. Ready to move on? Okay. So, how about no more high school figure? I mean, it's still high school figure, but we're going to make a nice, creative combination of high school figures here. So, let's now call it number one. Okay? So, the number one, the base is a semicircle. Right? Semicircle. You guys want to name a radius for a circle?
3.
3. Thank you. It's a semicircle of radius 3. Okay. So the base itself is a semicircle with radius 3. So let's draw the figure. So that's why I'm giving us some kind of good amount of space right here. Think about it. And we don't need axes or anything like that. But as a space figure, is that okay with you being a semicircle in a space perspective, Rita? Okay? And so the radius 3, so the center is there, radius 3 is, this is 3, okay? Good so far? Okay? And so now, each of the parallel slides, right? This time I have to go even a little more. Okay? Each of the parallel slides are perpendicular to the diameter. Perpendicular to the precise term is called the great chord. Have you guys heard of this one? Actually, it's a classical, I mean, a very old term. When you're looking at a circle, people in these days tend to call that diameter, right? Ladies and gentlemen, the truth is diameter is the length of that.
It's half it.
The real, that's nice equator line there. The truth is it's called the great chord. Because anywhere here is a chord, right? The actual figure is called a chord. That segment that connects it, any 2 points on the circle is called a chord. But then that biggest chord is there, right? The length is the diameter. You see what I'm saying now? So measurement is the diameter, but then that thing itself is called a great chord. Okay? So, but I mean, if you don't like that, just take that with you as the equivalent meaning of the diameter. How's that? I don't know why these modern day, people kind of tend to chop out some of the precise wording and make it shorter. But anyway. So the description here says that each of the parallel slices, right, is perpendicular to the great chord, and then being also again being the isosceles triangle with can I still take that in height to whoever suggests that for me, right? Let's take the same. You want to say now? So what do I mean by each of the parallel slices is perpendicular to the great chord? And of course the slice is already standing up perpendicular to the whole base, right? So we don't need to argue about that. But the idea is when you draw that slice here as a stripe right here, and it's like that, right? That's what I mean by being perpendicular. Make sense? Okay. And then so on top of that, right? On top of that, we draw those triangles, those isosceles triangles. You see how it changed the figures already? That's the idea of that. So your slice, of course, standing up perpendicular to the base, but also perpendicular to that great chord. The great chord is here. Sounds good? And we got a triangle standing up to that. Okay? Do you expect the same size triangle every single time?
Not really.
But we got a height too. It's got a fixed height. It's got some fixed height, but it changes differently. I mean, my drawing here is a little upscale as well. It's got fixed height. Great for each one of those. It has a height 2. So height 2 is all over. Height 2. But then because we place the stripes here along this circle, the base of the triangle gets small, gets large, depending on where we place the stripes, right? Are you seeing that? Right. And so now as we get into solving the problem here, The idea now is that you're gonna put that on the x and y axis system again. Right? There's your x axis, there's your y axis. And I should have made it a little longer this way. Okay. But then think about in space setting right here. -3 is there, 3 is here. You guys follow it? Right. Then your circle kind of come out like that. Because there's a space, I think there's a floor, some imaginary floor going this way, right? And just your axis go that standing straight up, we call it some magical y-axis. It's not even important, see what I'm saying? No, it's not even important. Right? But so now think about each slice here. Each slice is being placed at some x value, do you agree? Right? But in a way how it looks, now, once again, what's the thickness of your slice? What do you see beside the thickness of your slice? Yeah, still the x, right? Easy enough to recognize. Yeah?
For your photo on the left, why is the triangle outside the semicircle?
Outside. Because it's standing up. Because it's standing up.
Oh, okay.
So of course, yeah, the circle is only on the base. Like you are standing right now straight up from the triangle on your 3 feet, right? So of course you're outside of the triangle. See what I'm saying?
Yeah.
That's the idea.
I think I was like thinking about it in like 2-dimensional, but it's like a
It's a 3-dimensional thing now.
Yeah.
And so back to the thickness of the slice, right? Yes, it's thickness dx. You guys follow it? Okay. And then we got a constant height here being 2, right? Height equal 2. So anywhere you place your slide here, right? That triangle got to maintain the same height, right? Being 2. But now you've got to be aware that height here being 2 again. But you got to be aware this base of the triangle is not the same. It depends on where you put that on the x-axis. See what I'm saying now? That's the idea right there, right? And so I'm going to need to erase some of that. That's why I kind of hesitated earlier to use this space here. But now since you guys had it all written down, let's erase it to make space. All right, so now let's figure out the cross-section area, right? Or just the area of the slides here. Cross-section area. Okay, let's figure it out. So again, triangle is always base times height times 1/2, right? And you already have the base. I mean the height being 2, agree? But the base here is, as a matter of fact, the base here is the length of the base here is determined by where we put the slice on the x-axis, right? Because if you put the slice here at some other x value, then it's going to be maybe some long one, right? And then when you put it here, it's going to be some short one. So the base, in other words, what I realize here is the base here is some function depending on x, where we put the slice, right, on the x-axis. You guys follow it? That's the idea. Right? So now with this base, let's figure it out. In the end, more specifically for the problem, now that the base, right, the length of the base depends on the shape of our circle. Am I correct? Because if you treat the shape of the circle here as a function of x, then wherever you put that on the x, it hits the function boundary, right? It hits the base boundary right there. So now, for a circle that you purposely put on the x-axis like that, the semicircle and the radius 3, and so we have our choice of putting it center right at 0. It's completely under our control right there. But think about each of the slides has to look like this. So how do I determine the height like that? How do I determine that length? Your circle, any circle with radius 3, right, and center at 0 is famously x squared plus y squared equals 9. You guys remember? Right? And so that means y squared equals 9 minus x squared. Follow it along? And that means y equals 2 choices, plus and minus square root of 9 minus x squared. Which one is this one? The positive one, right? Because the y value is going to be positive. We place our triangle that way. I mean, we place our base that way. It was our choice. So it's consequently brought us into this choice. Are we good? Right? We're taking the positive one, right? Good with that, like that? All right. So now, that's what I'm looking at again, right? So the base right there being the square root of a 9 minus x squared. Right? So putting it together, right? The area is volume here. I mean the volumes of one section is going to be 1/2 times 2, which will eventually cancel, times the square root of 9 minus x squared times the dx. We're good there? Okay. That's the volume for one slice. But now we're going to be accumulating. Where are we accumulating? Where's the starting point of our accumulation? -3, that's right. What's the ending of our accumulation? 3. Yes, I agree. So that completes our integral setup. Setting up. So in that way, what do we have for this? Now, 1/2 cancel with 2, right? It gives me just precisely a 1. Okay, so the integral reduces down to a -3 to 3. And square root of 9 minus x squared dx. Okay. So finishing out this integral right here will get us the actual volume, right, after accumulating all these areas. You guys agree on that still? Okay. Now the question I have, admittedly at this level that we've learned in terms of getting the antiderivative for this, we didn't learn the technique specifically for this problem yet. See what I'm saying now? But hey, gladly we can see this as, I mean, just seeing that strictly as an integral problem. I mean, we understand the ultimate purpose is to get the volume of this accumulation, okay? But now simply just looking at this integral over here, it's the area of that semicircle, right? It's relating back to that assignment you guys done a little while ago, right? That we're interpreting an integral as an area. See what I'm saying now? But the idea is, again, getting the antiderivative according to the fundamental theorem of calculus work is not possible yet at this point. Okay? We will learn the specific technique for that, but it's going to come a little later in the learning time like that. But this now, since we don't have that antiderivative ready yet, right? We're going to just see this as the area, the accumulation of the area for this upper semicircle. Okay? So what's the area there? The semicircle here has radius 3, right? And so the final answer comes out being what? 3. I mean pi times 3 squared, pi r squared, right? But then it's a semicircle, 1/2. See that there? Right. So 1/2. So in the end, it's going to be a 9 pi over 2. That's our final answer for that. Right. So 9 pi over 2 is the area of the base, and it's also the area of the whole volume of these. I mean, the answer to the whole volume of these accumulated triangle slides on top of that. Are you guys agree on that? Yeah. Don't get yourself confused. I'm talking about the area of the figure because now we are down to that step where we are only handling an integral problem. Okay? Right? Then this integral problem can be understood as the area of the semicircle. But then the overall purpose of coming up to this integral was to get that volume after the accumulation. Okay? So let's do another one, shall we? And this time, every example has its own specialty, so I can't really do part A, part B, and part C anymore. Okay, so calculate the volume of the solids, right, with the following description. The base is a semicircle, radius 3 again. Okay. Semicircle. Base 3. All the slices are perpendicular to the breakpoint, just like that, right? Then on each slide, we draw a standing up right isosceles triangle. See what I'm saying now? So it stands up like this. And so now being the right isosceles triangle, I don't have to come up with a fixed height because the height here is always the same with that line. Right? Being a right isosceles triangle, and the further description says the right angle, using that word, the right angle. Right angle, right? On the breakpoint. So let's put it in the axis system right there. And honestly, I don't even need the y-axis. It's just there for dummy reason. Or you can think about you put your y-axis going this way as well. See, there's the x-axis, there's the y-axis, right? And your semicircle minus 3 is here, 3 is here. Putting it like that. See what I'm saying? Up. Okay. And then so each of the slides here has to be, of course, parallel with the y-axis, right? But we draw a right isosceles triangle standing up like that. So that side is equal to this side here. See what I mean? Okay. And so the triangle here, the slice here is not the same size with the slide right here. You guys can see that now, right? It's not the same size with the slice right here. Right angle over there. See what I mean? It's still semicircle. And we have our choice to put that base to align with the origin to make life easier for us. That's all. Alright, so now once again, what's the thickness here of our slice in the way how we're putting it? Dx, okay. Simple, right? Here, that. What about the cross-section area? Cross-section area. Let's figure it out. So, isosceles triangle, right isosceles triangle, those are all triangles, right? So they got one fundamental, base times height times 1/2, right? So base times height times 1/2, so 1/2 times the base times the height. But this time, you notice that the base and the height are always equal right now, right? So that means it's going to be 1/2 times the base squared, right? The square of the base. And the base is what determined by the length on the base here is determined by this curve here, right? The boundary defined by the boundary of your the base region. See what I'm saying? That there's always a base region, right? And then so the length of the base region can run crazy like that, right? And then as we put slices there, right? See, short slice or longer slice is all depending on the boundary of your base region, how we put it. You know what I'm saying? Huh? And so the base region, we have a function for that. And so now, depending on where we put the slice, at some x instance, right? At some x value, the slice being placed there is going to be a function depending on x. So what is that function? It's a function of being this semicircle with them. So we've had that similar argument from the earlier example. So here I'm talking about 1/2 times, right? In parentheses, now we have square root of 9 minus x squared. Anyone questioning how I got this so far? We're all good, right? But then this time we square that, you know what I'm saying that? And then multiply with 1/2. So that is a formula for this problem to get the cross section anywhere. You've got the cross section's area anywhere you put your slide, right? At any x values that you put your slide. Okay. And so in this case, again, now you got once you identify the thickness and the cross section's area, right? Those are two completely clear steps, right? Now you're going to multiply the cross section's area 1/2 times that square root of 9 minus x squared again. And with the square, and you multiply with dx, right? Sounds good. And then now you got the volume for one slice, right? We're going to be accumulating all slice volumes from -3 to 3 again, right? That's how we're going to get the total volume. Let me know if there's anything I need to clarify more anyway. And so this integral will turn out a lot easier than the other one. We can come back and work with the fundamental theorem of calculus like that. But any problem that I hope you guys learn, it's not about we focus on how we do the integral anymore. It's about we apply the integral right into the work again. Okay? And so how we handle the integral may vary in different problems. Like that. We bring 1/2 out front, the integral of -3 to 3. With a square, you cancel with that square root, right? But in this problem here, surprisingly easy. 9 minus x squared dx for the integral. So when it comes down to the integral level like that, right, and we're going to have to just mix in every little techniques that we've learned up to this point to solve it, to calculate the integral. Right? The more important work is how we set up the integral. That takes the art to that, right? And the creativity of that. Right? But now, so for this problem here, And see, now this is how we're handling it. Don't you guys realize just as a function itself, right? It's an even function, right? Right? And so this is being an even function. So you can, and it's an even interval as well, right? So you can purposely write that into, see, 2 times. It's a 1/2, but then it's multiplied by 2, right? 2 times with the integral from 0 to 3 only. See what I'm doing there? And then 3 minus x squared dx, right? And so thankfully the 2 here cancel with the other 2 as well, right? That 2 cancel with the 1/2, right? And so I'm going to erase that little extra drawing right here to make some space for my work. Right? So here's my remaining corner of the board here. So that integral becomes, the 2 cancel already, so integral from 0 to 3, right? And it's a 9 here actually. Right? 9, yeah. So 9 minus x squared, right, dx. So that's now making it 9x minus 1/3 x cubed, right? We're evaluating it from 0 to 3 again, right? So that's making it quite easy for the calculation. 18. That's how we're calculating the volume using the slice method, right? So we've got a description, but of course, in these problems, we have to read and follow closely with the description of our solid, okay? Especially the description on the slices, okay? On the cross-section slices, okay? But the idea, again, the important fundamental is that we always gonna multiply the cross-section area, right, with the thickness. Okay? Multiply the cross-section area with the thickness, and then we're accumulating, because multiplying the cross-section area with the thickness, that gives us a volume for one slice, right? And then we're accumulating all of the slice volume from some beginnings to some ending point. That gets us the whole volume. And then these are some fundamental requirements. The slices have to be perpendicular to the base, right? You are saying that? And then further on, the slices are always parallel with each other, And then each slice is some kind of figure, and then all slices are gonna be the same kind of figure, right? They can be all rectangle, they can be all triangle, and triangle, they all have to be the same kind of triangle, right? It's not like it's also a triangle here, and the next one is the what do we call it again? Equilateral triangle, okay? It's not gonna happen that way. I mean, maybe in some near future, we're also going to learn, but probably not in this class, that the figure of the slice is changing pretty crazy like that. We don't want to do this in our class here yet. Okay. Any other questions for you?